Okay, in this lecture we're going to talk about SciPy, or specifically the SciPy library. It's often, the word SciPy is often used to describe the entirety of the Python scientific computing ecosystem. So that includes NumPy and Matplotlib, which we've already talked about, as well as the SciPy library, and we're going to talk about the library in this lecture. So the SciPy library is a collection of mathematical algorithms and convenience functions built on NumPy data structures. So it's tightly integrated with NumPy. We can feed NumPy data into these algorithms, and they'll often return NumPy arrays as a result. There's several different sub-packages. I have several of them, or many of them, listed on the next slide. I'll talk a little bit in general about what each of them are. And of course, like I said in the introduction, it's the combination of NumPy, SciPy library, and Matplotlib, which together kind of reproduce the functionality of MATLAB, at least on the algorithmic side. So most of the libraries in SciPy are organized into these special submodules. So the SciPy special or special submodule is one where you have your special functions like Bessel functions and things like that you need to evaluate. Integration, these are your numerical quadrature routines, both for integrating formulaic integrands, so the actual equations, as well as integrating data with like a trapezoid or Simpson's rule. Optimization, these are your minimization routines, of course. Interpolation, so this is splines and other things to interpolate scattered data. Fourier transforms, fast Fourier transforms and other things in FFTPack. Signal processing, linear algebra, this is all your both iterative and direct solvers, eigenvalue solvers. There's also sparse eigenvalue solvers, which a lot of the numerical routines here, particularly in linear algebra, are built on top of long, well-developed libraries like BLAS, BLAS, Basic Linear Algebra Services, and LAPACK, RPACK for eigenvalue problems, other things like that. Compressed sparse graph routines, statistics, so these are all your distributions and other things, random number generators, other things like that. Spatial data structures, this is your KD trees for doing nearest neighbor searches, as well as some common tessellations like Delaney and Voronoi tessellations of scattered data. Multidimensional image processing and file input and output, and there are a few more that aren't listed here. So in the next few slides, I have a couple of examples. I mean, we could essentially have an entire course just covering the algorithms of the SciPy library. So there's no point in even attempting to do that in a short introduction video. But we will cover a couple of different examples here in the next few slides. So integration, in this case, I've picked a very simple integrand. We of course all know that this integrates in closed form to 1/3 x cubed, and then we can evaluate it at 4, at the point 4. So in this case, we'll do it both using the built-in quadrature rule. So quadrature is just another rule for numerical integration. In this case, the argument to quadrature is actually a function. So we define an anonymous or lambda function here with the integrand, which is x squared, and then the second two arguments are the upper and lower bounds of integration, so 0 and 4. This returns two things, an answer and an estimation of the error. And in this case, it's 21 1/3, essentially to computer machine precision. And we can evaluate the integral in closed form. Again, we know this is 1/3 x cubed evaluated at 4, which we have here. The evaluation at 0 results in 0. So these two answers, the closed form answer and the numerical integration answer, are within machine precision of each other. There are also double and triple quadratures for area and volume integrals, different things, fixed quadrature routines like Gauss integration and other things, and then integrals for data like the trapezoid rule, Simpson's rule, other things like that. linear algebra, like we talked about. So in this case, we just created a random 3x3 matrix using NumPy data structure, and then we can use the SciPy linear algebra submodule to take the inverse of that matrix. We do here, and likewise the eigenvalues. In this case, it's prepared to solve for complex eigenvalues, so it returns the complex components. However, in this case, they're all zero. So these are 3 real eigenvalues for this matrix, and that just happens to be the case because it's a random matrix. I had no control over whether the eigenvalues were going to be real or complex in this case, because I used a random number generator. Interpolation. So here what we're going to do is basically generate some synthetic data, meaning data on discrete points, by first creating a range of numbers, x, that go from -1 to 12, and then evaluating the e to the x over 3. So e to the x over 3 evaluated at these discrete points, so -1, 0, 1, 2, 3. In this case, I'm printing x here. We could also look at, say, what y is to see, right? So this is the exponential. And the reason I basically started at -1 instead of 0 is because I just want this to pass through 0 so that I get the 0 data point there exactly. So then what I'll do is I'll take this discrete data, x and y, as we've seen, are discrete points, and we then interpolate using interpolate 1D. And what that returns is actually a function. So if we look at what f is, it's actually a function object that we can then evaluate at points. And in this case, to evaluate, I could have, say, plotted both lines, and you could have looked at what the evaluation is. But in this case, what we'll do is we'll actually integrate the function. So we'll integrate the function with quad, like we've already seen. In this case, we're passing in f just to demonstrate that it is a function. Previously, we used a lambda function in this case. And we're going to integrate it over the interval 0 to 10, and we see that the value is 2.919. Likewise, if we were to integrate via Simpson's rule the raw data, again on the interval 0 to 10, that's what we have here with Simpson's rule. The integration is 2.89. So I'd have to I would say that we'd have to integrate the function exactly, the original function, to know what the right answer is. In fact, I think we could do that here. So let's just do and so there we have the integral of not the interpolated function, but the original function itself is 2.89. So in this case, there's just some small error because we're interpolating a function and then integrating that. But nevertheless, just to demonstrate how the interpolation works, along with reiterating the integration here. So again, I only have a couple of examples here because each of those submodules would take weeks to discuss in detail. And the purpose of this was just to demonstrate the kind of idea of types of things you can do with the SciPy library. I'll leave it to you to research the individual modules in more detail. Now, part of what we're going to do in the PGE 310 class is spend the rest of the semester actually digging in to the numerical algorithms that are associated with each of those submodules. So we'll look at the actual structure of the algorithms and what they're doing, and then I'll discuss the SciPy implementation of those along the way.